Number 4. So if the FG is a gravitational force on an object, then that should be the weight. If you consider the M1 to be an object and M2 to be the mass of the Earth. So if we, here it says, so set FG equals mg and calculate the acceleration due to gravity. So let's take a look at this. If we say FG equals mg, what we can do here is we can factor this FG out and replace it with the universal gravitation equation. So let's do that. We get big G equals M1, M2, all over R squared, and that'll be equal to mg. But because there's multiple m's, we're going to have to label this nondescript m as one of the two m's. So let's say m1 is the person's mass and m2 is the mass of the Earth. And if we do that, we see that the m1 can cancel off both sides. So we're left with G equals m2 over r squared, and that's equal to G. Now, if we plug in what we know that big G is 6.67 times 10 to the negative 11th. The mass of the Earth is given over here in this useful information thing that you might want to keep handy for some of the problems you might see later on. The mass of the Earth is 5.97 times 10 to the 24th kilograms, which is a lot of mass. And we'll divide that by the radius of the Earth, which is given here at 6.38 times 10 to the 6th. And don't forget that should be squared, and that will be equal to G. So if we plug that in, we get 6.67 11 times 5.7 times 10 to the 24th divided by 6.38 times 10 to the 6th squared. And we wind up getting an answer of 9.78 meters per second squared, which is very close to that 9.8. But a good question is, why isn't it 9.8? Shouldn't it be? And one thing we consider is when we use that number, the Earth is not perfectly spherical at sea level. And because of that, some areas, like where we're at, is a little bit further away from the center of the Earth than like the equator. So the further north or south you go away from the equator, the heavier, the higher the G is going to be, just by a little bit. But at the equator, it's probably around 9.78. So that's why we just use 9.8. It's a nice average for working in physics. So that's that one. Right, and then 5, satellites use gravity to keep them revolving around the Earth, just like the Earth uses gravity to keep revolving around the Sun. Without gravity, these objects would fly off into space in a straight line, tangent to their motion. The orbital velocity of the object has to be just right to get in uniform circular motion. The orbital speed radius is radius dependent. So depending on how far you put out the satellite from the Earth, it needs to go faster or slower to make that radius work. The object is technically in free fall when it's orbiting. So when it is out there, it does appear to be weightless. But there is still gravity. It's just that gravity is only changing its direction. It's not really pulling you against anything. So that's why astronauts on the International Space Station are weightless while they're in orbit. There's a special kind of orbit called a geosynchronous orbit. Meaning that these a particular type of satellites will orbit around the Earth at the same rate that the Earth is revolving. So it almost appears as if the satellite stays at a fixed position in the sky. These can be really helpful for GPS systems because you don't want your GPS satellite to be over Saudi Arabia when you're trying to find your way to the next town over. That doesn't help you whatsoever. That's kind of the way satellites work, and we can look at them using some of the equations we've already mentioned. So to calculate the orbital speed, the gravitational force is causing centripetal acceleration. Calculate the orbital speed of a satellite. You can use one of these, this equation that we eventually derive here to do so. So we start off with the universal gravitational equation. So we have Fg equals. We start off with this scenario where we have Fg equals mv squared over r, since Fg is providing the centripetal force to this scenario. And if we use the universal gravitational equation now to substitute in for Fg, we get big G equals m1, m2, all over r squared. And we'll label this as m1 again, just like we did in our previous example. And a lot of things just cancel here. So the m1s cancel right off the bat. And an r cancels with the r squared, because it's over here, leaving with just an r. So when we cancel things out, we are left with G m2 over r equals v squared. So with a quick little calculation, or a quick little algebra move, we can root the sides, and we wind up getting v equals root big G m2 over r. So that equation can be used to find the orbital speed of a satellite. To figure out the period of an orbital, or of an orbiting satellite, you can use this equation again, v equals 2 pi r over period, and just solve this around. So if we want to try and solve the period, we can just multiply both sides by t, divide both sides by v, and get 2 pi r over v equals the period. So that's something we can use as well. Right? As we continue, let's do after that. Right, so another question. Let's look at how to use these equations to figure out the orbital speed necessary for keeping a satellite in a geosynchronous orbit. So just for the sake of time saving, the period here we know will be 24 hours because it's geosynchronous. It has to be the exact period. And the time-saving piece, that is the same thing as saying 86,400 seconds. So we won't do that conversion. So to get things started, this is going to be an interesting scenario because we kind of have two equations and we have two unknowns. So we're going to have to kind of use a system of equations business again. So flipping back over to here, we're going to use this equation, but I'm going to doctor it just a little bit to make it a little bit easier. So what we're going to do is use that equation, but just square both sides. So we get v squared equals g m over r. And we're just going to leave it as the mass of the Earth, just to make ourselves have a little bit of an easier time. The other equation we can use is the v equals 2 pi r over the period. And what we need to do, we need to substitute the velocity from this equation, this equality, in for the velocity on this side. So what we'll do here is we'll just put 2 pi r over period over here, that is squared, so remember that, equals big G and E r. And if I carry out that square, if I do the distribution business, we get 4 pi squared over r squared, times r squared, all over period squared equals G and E r. And now we need to just do a little bit of doctoring. So what we'll do first is multiply both sides by r. We wind up getting 4 pi squared r cubed times all over period squared equals G me. And then we'll start moving things from here back onto the other side. So we'll divide both sides by 4 pi squared, and we get leave some space over here. We get r cubed equals big G ME all over 4 pi squared. We'll multiply both sides by the period squared. So what we get is this equation here. And then we eventually need to take the cubed root of whatever answer we get. But let's plug in first before we do that kind of business. So, plug in, we get r cubed equals 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th. We get 86,400. That's squared all over 4 pi squared. So let's do that. So what we wind up getting is this really big number as 7.53 times 10 to the 22nd. And to get rid of this cube, we need to take the cube root of that number. So doing so, I get this answer. R equals 4,26910.2 meters. That'd be 42,226,910 meters, which looks good. And keep in mind, we're talking about how far is that above the Earth, and we do know that the Earth's surface radius is 3.58 times 10 to the negative 7, well, to the positive 7. So if I subtract that number quickly, we get that this thing must orbit I'm making a small error here. The radius of the Earth is 6.38 times 10 to the 6th. So if we go back, and then subtract that radius of the Earth, this time for good, we do wind up with 358,46910.2 meters. So that is how far above the surface of the Earth that we need to place this object. That for future reference will just be 3.58 times 10 to the 7th meters, just to make our life a little bit easier. Now, going back up here to find the velocity, now that we have this this height, this radius, it becomes much easier. So we're going to put this number here, 4.22 times 10 to the 7th, in for the radius, because we're counting how far away from the sun of the Earth that has to be in this radius. We take 2 pi times this number, 4.22, times 10 to the 7th, and divide by our period, which is 86,400. And with that little bit of work here, we should be good for this problem once we do the calculation. And we get the orbital speed will need to be 3,068 meters per second, which is quite fast. So there is that one. We're going to pick up with the angular quantities in the next video, so just keep on scrolling and we'll get this thing done eventually.